Hello, I am Nakamunto Wanit.
I am Alexis Pister.
I am Gaël Richer. And I am Paola Valdivia. We worked with Petra Eisenberg, Jean-Daniel Fekete, and Christophe Prieur to propose our vast 2020 Minute Challenge 1 solution that we called GraphletMatchMaker.
We publish our solution as GraphletMatchMaker.github.io. You can see the video, the report, and live demo of our interactive tools in this website. In our solution, we combine multiple graph analysis and visualization approach to address three following tasks. The first task is comparing the graph structure between the template graph and candidate graphs. The second task is trying to find the best matching subgraph in the last graph. Finally, we combine our approach in the first two tasks to identify the suspicious group that may be responsible for the internet outage. We propose three visualization and analysis methods to compare the graph structure in the first task: node link diagram, graphlet frequency, and temporal profile. Next, I will explain how we use these two in our solution. The first thing we did with the graph data was creating node link diagram in d3.js to explore multiple kinds of nodes and edges in the graph data. Here is the screenshot of the tool. We represent different kinds of nodes in different shapes. For the location, we observe that there is a single location for the phone call and assume that it is the original location of each person. We encode the location as the node color. The edge can be selected from the checkbox panel. From this tool, we found that there are two groups in the template graph. The first group is connected by dense communication when we filter email and phone relationships. The second group is connected with the similar traveling patterns when we filter travel to relationship. You can see from the graph that most of the nodes are person nodes, and there are only one co-authorship and one product. Interestingly, that product connects with only one buyer and one seller, and they have multiple edges of procurement transaction as well as communicate by email to each other. Overall, compare the template with candidate graph. Graph 1, 2, and 3 seem to have the same pattern, but it is difficult to tell which one is the most similar to the template graph. My friend Alexi is working on Graphlet approach to figure out which candidate graph is the best match.
We studied the structure of the given networks using graphlets. Graphlets are small induced subgraphs composing any network which give information on the local and global structure of the graph. We used graphlet frequencies to compare the template and the candidates on a global and node level, but also to find potential matches in the big graph using the frequencies as a basis for a node distance measure. Graphlets can be of various sizes, directed or not. We mainly used undirected graphlets of size 5 for interpretation reasons. We compared the normalized graphlet frequencies between the template and the candidates. The Pearson coefficient shows the level of correlation between each candidate and the template. We can see that graph 4 and 5 have a very different graphlet profile compared to the template. In contrary, graph 2 has similar frequencies to the template, with a coefficient of 0.76. The most common subgraph is the same, which is a 4-size click with an additional node. Graph 1 and 3 are a bit less correlated, but are not that much different than the template. We also compared the graphlet frequencies at the node level. Although we can see some similarities between the graphlet frequencies of some nodes, it is hard to find specific identical pair of nodes between the template and the candidates. Graphlets allow a static analysis of the graphs, which are dynamic in our case. This is why Paola did a temporal analysis of the networks.
We analyzed the temporal activity for the graphs using visualization at different aggregation scales. In this visualization, we show the edges of each node as circles colored by edge type. For example, blue circles represent emails and orange circles represent phone calls. In this case, we see two peaks of communication in the template graph. But looking at the temporal activity of the other graphs, we notice similar peaks in graph 1 and graph 2, but not in graph 3. We create a time series for each graph by counting the daily activity. We can then compare graphs visually and also measure the difference in activity between graphs. In these aggregated views, the most similar candidates were also graph 1 and 2. Even though none of these graphs present an activity peak in the middle of the year, graph 1 and 2 both have an increase of communication, then a high peak followed by only travel activity. However, the peak activity from graph 2 is closer in size to the one of the template graph. Using the dynamic time warping distance, we calculated the pairwise distance of the aggregated time series between all graphs. According to this measure, graph 2 is more similar to the template graph. To match the nodes in the template graph and candidate graph, we used several similarity measures to find nodes that had the same properties. So far, we introduced graphlet similarity and temporal distances. Next, NatCommon will introduce two more similarity measures that compare demographic profiles and travel itineraries profiles.
For demographic profile, we look at the data and found that different financial categories have different range of value. As you can see, some categories like money income before tax, mortgage payment, and personal tax, highlighted in red box, have an extremely high value. We transform the data with the standard score to construct the demographic profile of each person node. Standard score allows us to see who spend or receive money more or less than the average of a particular category. Next, we calculate the similarity score between every two person pairs of the template and candidate graph using cosine similarity measure. For travel age, we construct the travel itinerary profile of each person as a set of tuples from source location to target location. You can see in the graph where we encode the trip profile of each person as a dot. We calculate the Jagged similarity coefficient of trips made to measure the similarity between two person nodes.
Afterwards, we tried to find good matches inside the large graph using pairwise node comparisons. We followed three different approaches, using seeds as a starting point for a crawling algorithm, focusing on specific patterns, and using a manual matching tool. First, we developed a greedy matching algorithm to find good possible matches from the seed, using any node distance measure. We first initialize a candidate set of nodes and fill it with all the neighbors of the seed using the communication channels. The pair of nodes which have the highest similarity value between the template nodes and the candidate nodes is matched. The candidate set is then updated with the neighbors of the latest matched node in the large graph. We repeat the process until all nodes of the template have been matched. We used several distance measures using demographics, travel, and graphlets. However, for the graphlet distance, the degree distribution is not the same between the template and the large graph. Thus, we cannot compare the node graphlet frequencies directly between the template and the big graph. To still compute a graphlet distance, we sampled a population of subgraphs from the big graph, with the same size than the template. Each node of the big graph appears several times in this subgraph. It was then possible to compute for each node a distribution of frequencies for each graphlet. But we can compare with the frequencies of any template node. To have a distance, we computed how many times the frequency of each graphlet for the node of the template was inside the distribution of the same graphlet frequencies for the node of the big graph. However, the majority of the template nodes are not included in all channels. For example, we can see that only a few nodes have communication and travel edges. Thus, we combine several distances together by using their means to find matches relevant to several channels at the same time. Here are the graphs found from seed 1 using various distances. We can see that a highly connected component is always found, similar to the one in the template. However, the rest of the subgraphs seem to vary. The graphs found from seed 3 look similar than with seed 1. However, this visualization only allows to compare the graphs globally. How to evaluate the extracted graphs in more depth?
To evaluate how good a graph match was and to compare strategies, we developed the node matching view. Each pair of match nodes is represented by a column with at the top the template node and at the bottom the candidate node. Each line of squares represents a distance computed between the match nodes. A dark blue square indicates a distance value of 0. The green arcs represent the retrieved edges of the communication channel, while the red edges are not retrieved.
Here are the two subgraphs found from the seeds 1 and 3 using a combination of the demographics and travel distances. This is the distance measure which gave the best results. The demographics and travel distance are very low, which shows that the matched nodes often have similar profiles. The graphlet distances vary more depending on the nodes. We can see that the two subgraphs share a lot of edges with the template, but a lot are missing as well.
To have a starting point for matching nodes in the large graph, we decided to focus on the buyer-product-seller pattern. In particular, we focused on the buyer, since it had connections with several other people and has also traveled to some countries. We visualize the ego network of the buyer, where we can see their in and out connections through time. We can see their communication exchanges and buying and travel activity. This is summarized in this other visualization, where we use different glyphs for each edge type. We counted 9 transactions for this person. So we decided to search for buyers on the large graph. And we focused on the 3 candidates who bought at least 7 products from the same person. We compare visually each candidate from the large graph with the buyer from the template graph. We use a heat map to compare the demographic profile and aggregated temporal bars to compare their activity through time. In this case, the first and second candidates are bad matches. The third candidate's demographic profile and the template node's profile were very similar. Even further, we noticed that there was a one-to-one correspondence of the purchased products, and that the travels from the template node were also in the candidate. We concluded that this is a good match. From these observations, we knew demographics profile and travels were a good way for finding matching nodes on the large graph. So we extracted the nodes with matching demographic profiles and added all the edges between them. Then we added the nodes with matching travel patterns. This view that we introduced before shows the agreement between the template and the final match. Even if there are some differences in the travel distances, overall, the final match is almost perfect relative to communications between people. The phone locations, represented by the color of the circles, is also perfectly matched, and the distance between demographic profiles is very low.
We've seen that building an efficient crawling strategy using distance metrics is difficult. However, in some cases, nodes can be visually matched with confidence, and metrics remain useful to narrow down the number of possibilities to look at. This motivated us to build this manual matching tool using both distance metrics and visual representations. In this example, we start with a candidate graph extracted from the large graph around the buyer-seller pattern. On the top, we see summary views for the template graph, one showing the structure, the other showing temporal activity. On the bottom, the views are the same, but for the match graph. Initially, the match graph contains the buyer-seller pattern plus the country nodes. On the right, a table shows the list of possible node pairs with their distance along multiple metrics. We start by looking at node 47 because it is connected to the match nodes and also involved in a pair with promising results. By clicking on the pair, we can inspect its similarity through detailed views that appear on the bottom. We see that the demographic heat maps are highly similar and that there is a shared pattern of communication events in the temporal bars. The views on the right look at the consistency of communication neighbors. Here, the inspected pair is in the middle, and the two outgoing arcs are green and red, which means that the pair is consistent with one of the neighbors in the template. Overall, this pair seems like a good match. After accepting this pair, the table and the views on the left update to reflect the addition. Here, after matching some more nodes, we identify an interesting pair involving node 41. Since this node has several travel activities, we choose to filter the table to focus on it and sort the table according to travel similarity. Then, we inspect the two best pairs in detail because they have more promising travel scores than the others. We validate the first one because we are able to recognize the travel pattern around December on the temporal bars. To sum up, the tool allows to focus on node pairs based on different information. The node link diagram and temporal views show graph and temporal activity patterns, which can be used, for instance, to focus on unconnected nodes, a node connected to matched nodes, or a node with many travel events. The tables allow us to focus on node pairs with promising score along one metric or another. Then, we can validate or reject node pairs after detailed inspection and iteratively compose a match for the whole template graph.
Next, we apply visualization we developed to identify the group that may be responsible for the internet outage. To identify suspicious activity on the extract subgraph, we visualize aggregate time series and we saw a sudden peak of communication in November. That led us to explore further what happened. Using the heat map plotting between day and hours, we observed that this peak happened after there was no communication for several days. Surprisingly, exchange of email and phone call in the 2 following days. So we look at the connection between people before and after the outage. We observe a dense communication aid by both phone and email among a group of people 2 days after the event. So we suspect that those people may be responsible for the outage. In conclusion, we apply multiple data analysis and visualization techniques to address WAS 2020 Mini Challenge 1. First, to compare the graph structure, we propose node link diagram, graph bed frequency, and temporal profile to evaluate the similarity between graphs. Second, to find matching subgraph in the large graph, we use node similarity measure to find matching node, and found that demographic profile and travel itinerary led to a good result. Based on this finding, we developed a tool to manually compose a match for the template graph. Finally, we show that our approach for the first 2 tasks can be combined to identify the suspicious group in the large network. We thank the committee chair and reviewer for the award to this work, and thank you very much for your attention.